Hello everyone, welcome to this talk about our recent work on a generic framework for Byzantine-tolerant Consensus Achievement in robot swarms. This is a collaborative effort between our colleagues in Canada and Belgium. When robots in a swarm without a centralized controller want to collaborate, they need to achieve consensus. The consensus could pertain to a set of actions, the state of the external environment, or other information. However, achieving a consensus is not a trivial task in a decentralized swarm. For example, these three robots want to agree on the location of the blue circle. The presence of Byzantine robots, that is, robots that provide wrong information, may prevent the swarm from reaching a consensus. For example, even though the information from the green robot is correct, a malicious red robot might intentionally share inaccurate coordinates to mislead the swarm. Also, the blue robot might try to reach the spot indicated by the green robot, but fail due to its self-positioning fault. In this basic example, we can see that the robot swarm cannot reach a consensus on the location of the blue circle due to the Byzantine behavior caused by faults and malicious tampering. Blockchain and smart contract techniques offer a promising avenue for robust consensus achievement in robot swarms. Our co-author, Dr. Strobel, demonstrated this concept using a customized blockchain system for consensus achievement in a one-dimensional value space. Then engineer Pacheco constructed a practical blockchain meta-controller in a real multi-robot system. However, existing solutions in this field are task-specific and cannot identify different Byzantine behaviors. In this paper, we propose a generic framework to achieve consensus in a robot swarm in an arbitrary task and observation space. Our framework can be described as being organized in 3 stages and composed of 3 customizable modules. The first is the proposition stage, where robots submit reports for the observations that they believe should become part of the consensus. Each report contains a deposit equal to a fixed portion of the robot's current assets and a binary voting decision. Reports are clustered by the clustering algorithm on the smart contract, and each cluster forms a proposal. Given these proposals, robots perform actions to verify them, such as move to and walk around the target positions. Then they submit reports to express their opinion to confirm or reject the proposal. It's worth noting that, despite having different motivations, reports made in the proposition and verification stages are structured transactions with the same format. It is the clustering algorithm on the smart contract that clusters reports and requires further verification of the outliers. Then a weighted voting game is conducted in each cluster. Its outcome decides about the inclusion or not of each proposal in the consensus. Based on the game's outcome, a reward distribution rule redistributes the robot assets from the losing to the winning coalition, reflecting the kind and severity of the Byzantine behaviors. Using this framework, we have implemented a concrete solution for Byzantine-tolerant consensus protocol for the problem of identifying the number and the locations of food sources in a foraging task. Here, we have used an incremental k-means algorithm and a weighted voting game based on deposit amounts. An equitable reward distribution rule then reallocates deposit from the losing coalition group to the winning one. A comparison of our method with 2 established consensus protocols shows that our method consistently achieves better consensus quality, even in the presence of faulty or malicious robot behaviors. However, robots must perform repeated sampling to filter out abnormal proposals. And because assets are redistributed among robots according to their behaviors, they can be used to identify Byzantine robots. The allocation of more assets to more reliable robots increases the amount of deposit in affirmative votes to genuine food source locations. This enhances the system's robustness against false rejections. Moving forward, we are applying our framework to real robot tasks, such as the RGB color consensus problem affected by physical camera perception variations. We are also applying this framework to simulated multi-robot SLAM tasks, where the smart contract meta-controller guides the swarm to build high-quality mapping. This project is an outcome of a bilateral cooperation between Quebec and Brussels, with support from academic institutions and financial sponsors from both regions.